and welcome to the lesson or discussion on proofs by contradictions, parallel lines, and transversals. And really, here, proofs by contradiction is in its own category. So I really should label it like this, like proofs by contradiction is like its own category, and then we talk about parallel lines and transversals. In other words, we're going to use contradictory proofs to prove things about parallel lines and transversals. So first, let's look at the definition here. It says a proof by contradiction. It's a proof, but we assume the opposite of what we're trying to prove, and then show that the assumption leads to a contradiction or a violation of some known theorem, postulate, or property. So instead of proving something is true directly using postulates and theorems and properties that we know, we assume the opposite of what we're trying to show and then demonstrate how the opposite thing is false, therefore the original thing must be true. So it's like if the opposite statement is false, then the original statement must be true. So if I say something that's clearly wrong, then the opposite of what I said should be correct. So now let's look at an example here, and this is probably something that you've seen in maybe in algebra or maybe even before that in elementary school. It says prove that division by zero is undefined or that it produces no answer. And I don't know if you remember, but I'm sure when you had this talk in elementary school or maybe middle school that there was maybe a little bit of debate and everybody says, sure, why does it have to be no answer? I can come up with an answer for it. Okay. Well, let's look at this proof, okay? And it's very hard to demonstrate that something doesn't happen. This is the hard part here, like produces no answer, okay? It's easy for us to show that something produces an answer. All we have to do is get the answer. But it's hard when we talk about like something, the absence of something. So we'll do this proof by contradiction. So we'll say 1, assume division by 0 is defined. Okay. So let's say I have some number. Okay. So we'll say that let x be a real number. And let's pick a value for x. So let's pick a value for, so let x be a 0 number. Maybe x is 5. Okay. And then divide it by 0. So we get 5 divided by 0 equals, and we don't know what this equals, okay? I don't know exactly what this is equal to, so I'll call it some variable. I'll call it y. Okay. So 5 divided by 0 equals y, equals some value. And so here, there has not been any contradiction yet. Everything we've done so far is perfectly legitimate. But let's see what happens after that. So in step 4, we're going to say multiply both sides by 0. So we get 5 over 0 equals y, and then times 0 here, and times 0 over here. Okay. So now we get these zeros cancel. Okay. So we get 5 equals, and y times 0 is just 0. So we get 5 equals 0. And now here, this is a contradiction. And we usually, sometimes in math books, you'll see the drawing of 2 arrows pointing at each other. That's kind of the symbol for contradiction. And this violates a certain property. It violates the reflexive property. Because the reflexive property says that for every real number, every number is equal to itself, but here we've demonstrated that 5 is not equal to itself, it's actually equal to 0. So there you have it, that is the contradiction. So I'm going to write the last part over here. Sorry, this is a little bit all over the place, there's not a lot of space here. But, so, because the assumption in step 1 leads to a contradiction, the opposite of the assumption must be true. So the assumption says assume division by 0 is defined, and it leads to a contradiction. So the opposite of that must be true, which is that division by 0 is not defined. Alright, so and I hope you can see here, this again is very different than everything else we've done, and it's actually a very powerful and useful method of proof because it lets us show the absence of something. Okay? And this is an algebra example. I'm going to end this video here, and then we are going to take a look at a geometry example.